Dwaipayan Mukherjee is an associate professor of electrical engineering at Indian Institute of Technology, Bombay. He received his BE in 2007 from Jadavpur University, Kolkata, in electrical engineering and M.Tech in 2009 in control system engineering from Indian Institute of Technology, Kharagpur. In 2014, he completed his Ph.D. from Indian Institute of Science, Bangalore, in Department of Aerospace Engineering. From 2015 to 17, he was a post-doctoral fellow at Faculty of Aerospace Engineering, Technion, in Israel Institute of Technology. His research interests include multi-agent system, cooperative control, and control theory. With that, I now invite Dr. Mukherjee to begin his presentation.
So I'll see how this goes. Incidentally, I know the reminiscence sessions are reserved for tomorrow, but I can't help but talk about this. So I kept pushing the preparation of these slides back till as late as I could, until last night I was occupied with that wonderful little souvenir that you guys have published. And I was so engrossed in reading them that soon it was midnight and I realized I hadn't prepared a single slide. So I said, okay, fine, I'm now experienced, I'm teaching courses regularly, I'll just do it quickly. But as it so happens, I don't generally teach from slides in my courses. So I'm still a bit slow at this, and I didn't realize. So I kept working on this until I heard the muezzin pronouncing the azan. And I was transported back 10, 12 years back, when I remember I would be sitting in this lab working, and suddenly I would hear this azan and feel, oh, it's morning. And then I'd suddenly feel the pangs of hunger and decide, okay, now I can't work for much longer, but I still have to wait for a couple of hours because the BMS won't open till 7. And then we would rush towards it and have a heavy breakfast and then go off to sleep. That used to be my weird routine. I hope none of you is following that sort of a weird life cycle now. Not that I've been able to keep it up, and probably for best, because as I was preparing this, I could see my concentration sagging, and you'll probably find a large number of typos. Please excuse me for them. But I'll try to make amends by writing the correct expression as and when I spot a typo over there. Anyway, so back to the technical part. So I'm going to talk about rigidity theory and formation control. Now this is a pretty old topic, especially rigidity theory. It predates formation control or multi-agent system paradigms by almost a century. It turns out that this rigidity theory owes its origins to chemists who were studying structures of atoms and molecules and were trying to see which of those structures are stable, which of them are rigid. And you see, intuitively we all understand what rigidity is. We know what a rigid body is. But in what follows in this talk, we will see that the idea of rigidity as we understand it can be generalized in several different directions. It so happens that this idea of rigidity that we consider ourselves to be familiar with is nothing but distance rigidity in the parlance of this multi-agent systems community or formation control community. I'm going to try and introduce a couple more concepts of rigidity, one which is called the bearing-based rigidity, the other is elevation angle rigidity, right? And we'll see that there is a unifying factor to all of these, and it fits in very nicely. So there is some beauty in sort of an abstract math. Now, if you appreciate that, then you'll just recognize it immediately, and otherwise it might seem pretty mundane and boring. And I've been accused of doing the latter, like boring my audience with the math and the gory details. So I'll try to avoid it as best as I can, but I hope you'll still find some of these things as interesting. Okay, so primarily this is where my work falls, at the intersection of these at the intersection of these three domains, which is graph theory, matrix theory, and control theory. And the main challenges in multi-agent systems stem from the fact that you're talking about large-scale systems. There could be a wide variety of interconnections, and scalability is often an issue. There can be delays and limited bandwidths, not just in the agents themselves or their dynamics themselves, but also in the communication channels. So all of these make the system way more complicated than just studying standalone systems in and of themselves. So of course, as I said, it involves graph theory, so a basic understanding of some notions from graph theory would be useful. So of course you understand pictorially, these are nodes and edges, but a graph is not really a picture, it's just a depiction. A graph is actually an algebraic object consisting of a set of vertices and a set of edges, which are nothing but a subset of the Cartesian product of the set of vertices with themselves. So these edges can be undirected or directed. In most of the work that I'll be discussing today, we'll be talking about undirected graphs. So we really don't care about the ordering of the vertices in the description of the edge. People normally call them ordered pairs. So you take Vi, Vj, but in our case, if there is an edge Vi, Vj, you also have an edge Vj, Vi, which is why we'll tend to put them in brace brackets rather than the parenthesis notation. So of course, these are also probably familiar to most of you. In fact, my introduction to all of this is through Professor Ghosh. I remember he had given us, again, this is a side note, an anecdote of sorts. So this was a course he had offered probably during my second year. I was still working on some problems on missile guidance, and I remember having a conversation with him when he said, you can probably work on something else, perhaps. I feel you might be better suited to it. And I was really looking for stuff, every other stuff. I was looking into interval polynomials. I was looking into PID control and some advanced techniques thereof. I was looking into MPC. And then suddenly at an opportune moment, he happened to offer this course, right? And all of us, those who were seniors to me, even they sort of attended this course. And he gave these, the first lecture itself, he introduced consensus, and he said, you know, this can be tailored suitably to get formation control. So why don't you guys write a code and present, and you know, submit it as an assignment? And you know, when he says something like that, he doesn't have to, as you all know, he doesn't have to really enforce something. But when he says something, you feel like it has got to be done. Even if you're not crediting the course, you will get it done. He has that spell on you. So we all did it, and we all used different kinds. So some people used M-file, some people used like commands in the command window. But nonetheless, everyone generated this code to get basic formation control from consensus. Now there began my foray into multi-agent systems, graph theory, and I read up some more papers. And in a matter of 6 to 8 months, I was actually working on problems in multi-agent systems. It's amazing. I completely switched tracks from guidance. I had a paper from missile guidance, and I was probably looking to build a thesis out of it, like missile guidance, but then I switched. So yeah, I mean, all this brings back a lot of fond memories. Yeah. So what I'm going to talk about today is not the consensus problem, but rather the formation control problem. Now, in my PhD, I mostly worked on the consensus problem, particularly under the directed cycle paradigm, the cyclic pursuit paradigm. But thereafter, during my postdoc, I also ventured into formation control. That's where I picked up these things. And again, owing to the excellent fundamentals that I had covered, again, courtesy of the man of the moment, that I really didn't have too much of a difficulty in picking up these concepts along the way. So the first thing that you need to understand for formation control in this is the idea of bar and joint frameworks. So what are frameworks? G is a graph which is described by a set of vertices and a set of edges. Along with that, if you embed them in a Cartesian plane or in maybe 2D, 3D, whatever is your ambient space, if you associate coordinates with each of those vertices, then that together with the graph gives rise to what is called this framework. A good way of studying these frameworks is through this bar and joint structure, or ball and stick, if you would. So you see, this is a particular graph, right? It's a graph with 4 vertices and probably 5 edges, right? But this same graph can give rise to multiple different frameworks depending on the embedding in the Euclidean space, right? So this is one framework for the same graph, and this is another framework for the same graph. So this would be called G with position P1, and this would be G with position P2. So those are the 2 different frameworks arising from the same graph. So this notion is going to be incredibly important to us. Why is it going to be so? Because in understanding rigidity, what we want to find out is, what does this encompass? What conditions have to be met in order to call something rigid? And when we say something, what is this something that we're calling rigid? Do we say that the graph is rigid? Well, not quite. It only makes sense to talk about rigidity when we are talking about the framework, right? For the same graph, you can have multiple frameworks, one of which is rigid, one of which is non-rigid. Now, what is rigid? There are also different notions of rigidity. In what follows in the sequel, I shall describe to you that the most useful notion of rigidity for our context of formation control happens to be that of infinitesimal rigidity. But before we get into that, let's get to the basic ideas of what are equivalent frameworks and what are congruent frameworks. So if you are given a graph and you build 2 different frameworks out of it, what do? You try to figure out the difference in the position between vertices, Which vertices? Those vertices between which there exists an edge, that is adjacent vertices. And you find out the distance between them. The norm is nothing but placeholder for the distance, right? You find out the distance. So if the distance between every pair of neighboring nodes in two frameworks are identical, then you say that those two frameworks are equivalent. All right? Now, you get rid of this idea of looking for only pairs of vertices over the edge set. Rather, look for all possible pairs of vertices in the graph. In other words, you can also think of it as a complete graph. So look at all possible, look at the notion of equivalence extended to a complete graph, and that gives rise to the notion of congruent frameworks. Why are these important? Because these are precisely the tools or the terms that allow us to define rigidity. So you see here, this is a framework, this is another framework. These two are equivalent because these black lines describe neighboring nodes. So there doesn't exist an edge between these two fellows. All right? So these two, if you look for only pairs of nodes between whom an edge exists, the distances are the same. However, there's no edge between this particular vertex V1 and this particular vertex V2 or their corresponding positions. And therefore, you see the distance between these two is not the same in these two frameworks. So they don't give rise to an unambiguous shape. In other words, if I were to specify to you the distance requirement that is to be met among neighboring agents in this graph, you cannot tell me for sure which shape I'm referring to. There's a non-uniqueness, there's an ambiguity. It could be this one, it could be this one, right? So this is the kind of ambiguity that we generally don't like. When we are looking for elegance, when we are looking for unique kind of results and solutions to problems, this is the kind of thing that really bothers us a bit, right? Now, there's this notion of global rigidity that comes in. What does it say? It says that a particular framework is said to be globally rigid if this equivalence, that is, if you look for only the edges and the distance, edge distances that is, then that itself will automatically ensure that between those pairs of vertices who do not share an edge, there cannot be any ambiguity. In other words, this particular framework is not globally rigid because here equivalence does not imply congruence, right? But this becomes too restrictive. For instance, in this graph is just one shy of being a complete graph. Sounds like a very restrictive requirement, isn't it? Because you're basically asking that everyone talks to each other, and only then you will have this global rigidity. Is it really useful? Just for the sake of this uniqueness, is it really useful? Let's think about this problem now for a bit. If you're already very close to a shape such as this, that is, this fellow probably needs to budge an inch or millimeter, whatever the distance may be, and gets to this shape. Now, once you have attained this shape, is it possible for you to move from this shape to this shape through a continuous deformation while maintaining these edge constraints? It is not. You can think of this as a handkerchief. Of course, a handkerchief is not rigid, but you can think of this as a handkerchief that's laid out on the mat. Now, you want to fold it back onto itself. What do you need to do? You cannot do it. If your entire space is like 2D, you cannot fold it back. You do not have the luxury of folding it back over the third dimension. There's a funny thing that people often say that ghosts are higher dimensional beings because they can sort of teleport themselves. So maybe there's a higher dimension through which they travel from one room to the other, right? Who knows? So this is like you'll have to ghost it out. Otherwise you cannot. While living in this plane, you cannot fold this back there. So is this really something that should really bother us much? I mean, if you're starting from a reasonable initial configuration that's closer to this shape, you'll probably end up here. That's what our intuition at least seems to suggest. So perhaps we do not require global rigidity as such. So let's look ahead and see if there's any other notion of rigidity that gets us to a reasonable description of the problem. So now we come to this simple rigidity. Okay? What does this say? So if you can read up the statement, and that's also clear from the statement, but I'll just try to explain here. You see that same shape here, right? So you can fold it from here to here, provided the distance between the corresponding vertices, or rather the positions occupied by the corresponding vertices in these two frameworks, yeah, is not bounded. But if you say that the distance between this and this, plus the distance between this and this, plus the distance between this and this, and the distance between this and this, if you want to restrict it to a very small value, then these two will not meet that criteria. Because it's only after this one is completely flipped over this. So the distance separating these 2 points is considerable. So if I choose a very large epsilon, well, of course, I'll be able to still meet that epsilon bound. But if I can always choose a small enough epsilon, so that within this small enough epsilon neighborhood, you cannot get any other alternate location of this position of the vertex V3 while maintaining this edge constraint. So therefore, although this is not globally rigid, yet this particular shape, this particular framework is rigid. Now, is that useful to us? Because, what is this epsilon value? It's highly dependent on that. So it's a case-by-case basis. You have to figure out what this epsilon is for a given configuration, for a given framework. We are probably looking for something a little more dynamic. But before we go to that, so you see, this is rigid as well as globally rigid. This is minimally rigid. I have the definition over there, but just to explain in simple terms, a minimally rigid framework is one where if you remove one edge from it, you lose the property of rigidity. So if you remove one edge from here, any one of these edges, you can remove this one for instance, and this one can just rotate about without violating the distance constraint. If you remove this one, you can just twist this into a rhombus, right? So it loses rigidity once you take out any one edge from that. So this is a minimally rigid framework, and this is not rigid at all. So based on the notions of rigidity, these are the different ideas you have. It turns out, however, we need a more dynamic concept of rigidity because we shall be concerned with designing formation control laws which will dictate, which will then govern the motions of these vertices, right? So this dynamic notion of rigidity is what gives rise to the idea of edge consistent motions and eventually infinitesimally rigid frameworks, right? So what is an edge consistent motion? I'll just take the liberty of using the marker here. So suppose you have PVI minus PVJ. So this is basically the inner product, but essentially it's the norm, right? It's the norm induced by this inner product. Now this is something, if Vi and Vj is an edge, forms an edge in the network, then this is the quantity that we do not want to change over time. Because now we are bringing in the idea of motion, so therefore we have to bring in the idea of time. That's what dynamical systems are all about, time.
What is the property of P?
Sorry?
What is the
P is the position assigned to vertex V. So it's that framework F, P, you can just say it is defined as G and P. So P basically assigns positions in the Euclidean space, whether R2, R3. You can also go abstract and call it RD, but it essentially assigns positions to every vertex in the graph. Right? Okay. So now this is the quantity that you want to maintain constant. So therefore you want the time derivative of this fellow to be 0. And immediately reveals something very interesting. Because it says, by the chain rule, it essentially says that PVI dot minus PVJ dot transposed, of course. Let's cut to the chase and get rid of these inner products. They are, after all, just a dot product. So this is PVI minus PVJ is equal to 0, right? What does this tell us? This tells us that if you want this condition to be true, either you have this fellow vanishing. But what is this fellow? This is basically the relative motion along the edge, right? So the edge cannot shrink, neither can it get extended, right? If Vi is moving with a certain velocity, Vj must move exactly in parallel with the same velocity, otherwise this fellow is in zero. There's another possibility. The other possibility is this fellow is orthogonal to this. So it's either a translation of the entire edge or it's a pure rotation, because this will generate a moment. Pvi minus Pvj is the edge position vector, and this is the edge velocity vector. So if the edge velocity vector is orthogonal to the edge position vector, it will induce a rotation. But this is for a single edge. If you stack together all of these edges that exist in the graph, then what you'll have is a set of constraints. And if you're now talking about edge constraint motions, then it's basically everything that sits in the kernel of these constraint equations and the rigidity matrix. What is the rigidity matrix? That's quite a bit to absorb probably in one shot. So what I'm saying is essentially stack up these norms which are to be constrained one after another. So suppose there are m number of edges, so there will be m such constraints. So it's a vector, it's an m tuple, right? And each of them is a function of these p's. Now, let's go to the next one. Yeah. So here we are. So now this is what it would look like. So this is your constraint set, and it has exactly as many constraints as the number of edges, right? Now, suppose you want to give it a slight perturbation, small incremental perturbation like delta p. So you can expand this like as a linear expansion and ignore the higher order terms. What you're essentially saying is that this should not change. So therefore, these two should be identical. What that means is that this delta p, these motions, should be in the kernel of this Jacobian matrix. As of now, we're just calling it the Jacobian matrix. But it is this Jacobian matrix that we'll define as the rigidity matrix. So essentially, we have now found a mathematical way to characterize our intuitively known notions of rigidity. That is, everything that's in the kernel of that Jacobian matrix, which we call the rigidity matrix, must constitute a pure translation of the entire framework or a pure rotation of the entire framework. So different parts of the framework cannot traverse at different velocities and cannot have different rates of rotations, right? So that's a rigid body motion. So if you study the characteristics of the kernel of this particular matrix, and you figure that the only degrees of freedom that are afforded to you are just translations of the entire framework and rotations, then you say that it is infinitesimally rigid. And this is going to be incredibly important to us. As you can immediately see, of course, the derivation is not as straightforward, but I can give you intuitive explanation behind this. In 2D, you have 2 degrees of translation and 1 degree of rotation. So you have essentially 3 taken away from here. And, you know, this is a Jacobian, right? So there are, it's an m cross 2n. If this is n, then it's an m cross. Yes, yes, sure.
Very similar to mechanism, the degrees of freedom is 0.
Yes. So here you give just those 3 degrees of freedom. You give just 2 degrees of translation and 1 degree of rotation. So that is accounted for by this. It's an application of the rank nullity theorem on this rigidity matrix. Right? Okay. So now this is some sort of an understanding of the rigidity notion as we know it in terms of distances. But before I go into this one of my favorite authors couldn't resist the temptation of putting it up there. But yeah, what I'm trying to say here is we should be very wary. It seems at this point that a good idea would be to have as many edges as possible. That only increases rigidity, right? It only helps in probably reducing the kernel size, the kernel dimension of the rigidity matrix. But most of these formation control laws turn up as gradients of some fields. And in case of these gradient-based systems, we need to study very carefully. The Lyapunov functions of the Lyapunov candidates present themselves very readily. But it turns out, I'm not going to get into the detailed derivation, it turns out that if you define a potential function as the sum of the squares of the errors in the formations, right, and you take their gradient and you negative of the gradient and you invoke that as your distributed control law, then it turns out that you should not have too many edges. Otherwise, you will be dealing with LaSalle invariance and you will not get anywhere with that. Because you do not want more than 2n minus 3 edges. So we are at a kind of a beautiful, we've come a full circle. On the one hand, we say that you want no less than 2n minus 3 edges for rigidity. On the other hand, for the purpose of designing a suitable gradient-based formation control law, you do not want more than 2n minus 3 edges. Otherwise, you lose rank, you lose positive definiteness of a matrix which is R transposed. Yeah? So the candidate Lyapunov function's derivative turns out to be something like this. Don't bother at the moment with what sigmas are. Those are state-dependent functions. R's are also state-dependent. But it turns out that this is what it turns out to be. So if you're increasing the number of constraints, you're making this matrix taller, and you're only going to add to the nullity of this, right? So there's a negative sign, I'm sorry. So you're only going to add to the nullity of this, and you're going to make life difficult for yourself. So don't add more edges than are necessary. So the ideal case would be have a minimally infinitesimally rigid graph. So this is all well known from the distance rigidity theory. 5 minutes? I'll quickly wrap up. No problem. At least I hope the rigidity notion has been made clear. What we're going to do subsequently is extend the idea of this rigidity to the idea of bearing rigidity, which looks nothing like conventional rigidity as we understand it. But that's the idea of doing algebra, right? We try to make things abstract so that even when things are not easy to visualize, we can still follow the structure and define new paradigms. So the bearing rigidity notion is very similar. It deals with projection matrices. So if you have a desired bearing like so that you want to achieve, and this is your actual bearing, the logical idea would be to rotate like this. So it's basically the negative of this will drive you in the correct direction to align yourself with the desired direction. So that's why the projection-based law is a very useful tool for designing bearing-based formation laws. But it turns out there is something deeper at the heart of it. I'll probably just quickly skip these things and get to the bearing rigidity. So what do you do with bearing rigidity? In exactly the same fashion as you had stacked up the constraints in case of distances, here you stack up the bearings. And that will be the size, right? Because bearings are unit vectors. So each of them is a D tuple. D could be 2 or 3 most likely, unless you go for abstract Euclidean spaces. And this is the number of edges. So the bearing, I've missed this subscript B here. So yeah, again, please ignore that. So this would be the partial of this. But it's exactly the same thing, after all. Masquerading as something different, but the mechanism is still the same. You get the rigidity matrix by taking the Jacobian of this constraint matrix with respect to the position vectors. And then you talk about what could possibly be the condition for infinitesimal rigidity. It turns out here you have also 3 degrees of freedom in part 2, 2 degrees of freedom corresponding to translations, 1 degree of freedom corresponding to not rotation anymore, because bearings would fix up your orientations. Now it's scaling. Now that's again something a bit of a bother, because you want to have a shape that also has a fixed size. So a square with sides 4 centimeters is quite different from a square with sides 4 miles, right? But in bearing-based formations, we do not distinguish between the two. So this is not seemingly very practically applicable. It turns out that these are the conditions for infinitesimal bearing rigidity on the bearing rigidity matrix. And here are some examples of frameworks that are not infinitesimally bearing rigid. But the good thing here is that if you ensure infinitesimal bearing rigidity, you'll at one go ensure both bearing rigidity and global bearing rigidity, because the two are identical. This is not true of distance rigidity. As we've already seen in an example, there are frameworks that are bearing rigid, but not, distance rigid, but not globally distance rigid. In this case, the two notions are exactly the same, right? So what's the problem with all of this? As I said, the scalability is a problem. So once again, we see that the attraction of bearings stems from the fact that bearings are easy to measure, easy to sense. But on the other hand, they do not fix up the scale or size of the formation, which distance does. So we combine the best of both worlds, and we take these elevation angles, which can be measured similarly to the bearings. But at the same time, if you're measuring the elevation angle and you're fixing up the elevation angle, you're also fixing up the distance indirectly. So that's what my student has worked on. He has extended this to elevation angles, defined the paradigm of this rigidity to elevation angle rigidity, and he has addressed a very interesting problem. You see, like we had said in that flexed, in the flipped ambiguity, right? We could flip it and still maintain the constraints in a rigid framework, but the shape would be completely different. So he figured that if you take these small little tessellations of triangles in 2D or small little, sort of pyramids in 3D, and you assign signs to them based on the cross product, based on their volumes and areas, and you maintain these signs, then you will not have those ambiguities. So in addition to stacking up the desired bearings or the desired elevation angles, you also stacked up a desired set of signs. So we, together with all of this, we have an extra number of constraints. So they're defined like, so again, I'll not bore you with the math, sorry, gory details. So now you have a big rigidity matrix. Few of those are corresponding to the elevation angles, and these are corresponding to the signs. If you maintain this, then you will be able to eliminate all possible ambiguities that might be there, right? So there are some interesting results, and I'll just quickly go to the simulation results. So although it looks like 2D and 3D are very analogous, they're not really so. 3D requires considerably more work because you had volumes and tessellations to choose from. So I'll again not get into those details, but the crux of the matter is that we have managed to solve a problem whereby, okay, the figure will do the talking. Yeah. So you see, prior to our work, people had specified a certain set of elevation angles, and they would start from the same location and get to a shape such as this, whereas the desired shape could be something like this. So once we have used this signed elevation angle rigidity notion and have invoked those constraints, we get the actual desired shape instead, right? So starting from the exact same initial condition in 2D or in 3D, we managed to get a desired shape without ambiguity because we have considered the signs of those formations. And a good part of this work is he's my first student to not actually work with me, but first student to graduate from my group is Chinmay. He has been the pioneer in this particular work, so credit to him. And also we had an ISRO funded project on formation control which drove us towards this direction. Thank you.